So in this video, we're going to talk about arc length and sector area. Before we do that, I want to make sure we recall a few things. First one is just that an arc is a piece of a circle divided by two endpoints. So if I pick an endpoint, call it A, I pick another endpoint, call it B, this little piece right here, that is called an arc. Up until now, we've talked about something called an arc measure. So this is where this gets a little tricky. The arc measure we've already talked about is the measure equal to the central angle that intercepts that arc. So if this is AB again, going like that, the measurement of this arc is just equal to whatever measurement we have here. So if this is 80 degrees, the measure of arc AB is just 80 degrees. That takes nothing into account of how big the circle is. It's just a degree measure, which tells us how much of the circle we are really talking about here. In a way, it can kind of give us that information of like how much, what fraction, what percent of the circle. Since we know the whole circle is 360 degrees, if I want to know what fraction of the circle, I can always just say, well, I know it's 80 degrees out of the whole 360. And then I could simplify that, right? I could say, I could even use Desmos to help me simplify that. If I take 80 out of 360, that's 2/9 of my circle, or about 22.2% of my circle. I want to know kind of what portion that is. I could also go backwards from that, right? If I knew that I had an arc that is, let's just say 3/5 of the circle. Right? Anytime in math that you see that word of, that's always a matter of multiplying, right? So I'm going to do 3/5 times a whole circle is 360 degrees, and that would tell me whatever measurement that is. 3/5 times 360. And so that would be 216 degrees. So if I had an arc that was 216 degrees, that's probably about that much. A little over half my circle, 3/5 of the circle would be 216 degrees. That's the measurement of the arc. We'll call it A, B, C. So that's the measure of a circle. Today, what we want to talk about is how we would find the actual length of that arc. So how far would you have to actually walk if you walked around it? And before we get into that, let's just real quickly talk about how we find the distance around an entire circle. If I wanted to start here and go all the way around the circle, what would I do? Well, that's called the circumference, and it has an area formula either of 2 pi r or pi times the diameter. Usually we have the radius instead, so we'll use that. So if the radius is 5 in this case, our circumference would be 2 times pi times 5, and we could either leave that as 10 pi, or we could go over to a calculator and go 2 times pi times 5, which is 31.4. That's the whole way around the circle. Now, if we combine those two ideas together, all we really want is some fraction of that total distance. So rather than taking the fraction of 360, we're going to take the fraction of our circumference. So the arc length is just a fraction of the circumference. It's the length in linear units, things like inches, centimeters, yards, meters, miles, whatever. But it's the fraction of the circumference, whatever fraction of that whole circle we have of the actual circumference involved. And so if I think about that, if I were to know that I had exactly a quarter of a circle, for example, well, I could just do 1/4 times 2 pi r. If I knew instead that I had a third of a circle, let's just say that's a third of a circle, I could do 1/3 times 2 pi r. It's whatever fraction I have times, of is always times in math, the circumference formula. Now, in general, I might not know exactly what fraction of the circle I have. It's not going to always be quite that nice. But what I will usually get is that central angle, that theta. And so to write the fraction, all I'm going to do in general is just say, okay, well, whatever theta is out of 360, that's my fraction of my circumference, 2 pi r. So that right there is my formula for arc length. It is just whatever fraction I have of the whole circle times the whole circle. So if I have 72 degrees, I would do 72 out of 360 times 2 pi r. That's all I would need to do. So let's go ahead and do an example here real quick. On this one, I've got central angle here is 60 degrees. The radius is 9. The first question I have for you is, what is the measure of arc PQ? And that has nothing to do with anything we've talked about today, because remember, the measure of an arc is just equal to the central angle. So in this case, the measure of the arc is 60 degrees. Now, if I wanted to know the length of arc PQ, that's when I need to actually use my arc length formula. So I would need to take my theta over 360 times 2 pi r. And then I can just go ahead and plug in my numbers. So in this case, I'd have 60 over 360 times 2 times pi times 9. Now I've got options here. I could, if I wanted to, start simplifying this all by my own, right? I'm going to put that off to the side here. 60 over 360, I can cancel out the zeros. 6 and 36 cancels out to be 1/6. 2 times 9 is 18. And then I've got a pi. Well, 1/6 of 18 is 3 pi. So I could do that all by myself if I wanted to. Option 2. I could punch that whole thing right into my calculator. 60 divided by 360 times 2 times pi times 9. That gives me a decimal answer, something like 9.42 if I round to the nearest hundredth. This one give me units? No. So this one's just units. I could also go somewhere in the middle, right? I could use my calculator to help me simplify it if I wanted to. If I just took that exact same formula, but just, 60 divided by 360 times 2 times 9. I just left the pi out. What I'm really doing there is I'm rewriting my formula with the pi at the end. I'm allowed to do that. It's all just multiplication. And then this part of my calculator says is 3, and the pi just hangs out there at the end. So 3 pi. I'm going to guess most of us are not going to want to do this entirely by hand, right? Use a calculator to help you out, either by typing the whole formula in and giving me the decimal to the nearest tenth or hundredth, depending on how it asks, or use a calculator to help you simplify that by just moving the pi to the end, doing all the multiplication steps all together on your calculator. One of those two options would be really good. Now, next up, we're going to talk about sector area. So before we do that, let's just review the area of a circle. That is how much space a circle takes up. You probably remember the area formula is pi times the radius squared. Now, sector area is just the exact same idea as arc length, but applied to area. A sector is just a little pizza-shaped thing. And just like with an arc, a sector is just some fraction of the inside of a circle. So all I have to do to calculate sector area is take a fraction times my circle area formula. And if I know that that fraction is really easy, like I see that it's 1/4 or I see that it's 1/2, I can just use 1/4 or 1/2. But in general, I can just go back to whatever my angle is. So if I have whatever theta is, doesn't really matter, times pi r squared. R is my radius. It's just whatever fraction of the circle I have times the area. And that fraction is being written as some angle out of 360 degrees. So we'll go ahead and do a couple of these together here. So if I wanted to calculate the area of that sector area, I'm going to use my formula, theta over 360 times pi r squared, and I'll plug in my numbers. 60 over 360 times pi times 9 squared. And I have the same exact three options as last time, right? I can do this kind of piece by piece using order of operations. So if I wanted to do that, I would have 60 over 360 times pi times 81, because 9 squared is 81. I could simplify that. I'd have 1/6 times, I'm going to go ahead and put the 81 first, 81 pi. Well, 1/6 of 81, I don't happen to know what 1/6 of 81 is. Turns out it's not super nice, but it's 13.5 or 27 halves. So I could leave it as 27 halves pi or 13.5 pi. I could do it that way. I could go step by step, use my order of operations, exponent, simplify the fraction, multiply together, then write it in terms of pi. Option 2 is the same as before. I could just punch this whole formula right into my calculator. That's really easy. I'm just going to do 60 divided by 360. I'm going to multiply by pi times 9 squared, and I get 42.41. I'm going to pause here and just remind us this is area now. So I'm going to talk about square units. And then kind of somewhere in the middle, if I wanted to leave this in terms of pi, but maybe use my calculator a little bit more to make this job a little bit easier, all I'm going to do is just move the pi to the end. So 60 over 360 times 9 squared times pi. And I'll just type this first part right into my calculator. So 60 over 360 times 9 squared gives me 13.5. And I could leave it as 13.5 pi or 27 halves pi. And still units squared. So either option. I would generally not do a decimal times pi, but one of those two, either using your calculator and give me a rounded answer where it's appropriate, or using your calculator still to help you get answers in terms of pi. If you really like doing things by yourself without a calculator to help, go for it, but I don't think that's necessary. Okay, last one we'll do as an example here, just a slightly different number. Just a reminder, we're doing all three here. Measure of the arc, length of the arc, and area of the sector. So you can pause and think about those if you want. And then let's go ahead and talk about them. The measure of the arc is just the same as the measure of the central angle. So in this case, I don't need to do anything to answer that question. It's 135 degrees. That is the measurement of the arc. If I want to find the length of the arc, that's where I've got to use my fraction times my circumference formula. Theta over 360 times 2 pi r. I'll plug in my number, 135 over 360 times 2 times pi times 12. And I don't think this one comes out nicely, so I'm just going to go ahead and type the whole thing in. 2 pi 12. So I get 28.27. That's my arc length. If I wanted that in terms of pi, remember I just move my pi to the end and type it in. So what that would look like would be 135 over 360 times 2 times 12. And it would help if I typed the right numbers in. And so yeah, that actually does come out really nice, right? So I could also write this as exactly 9 pi. And then for my sector area, now I'm finding the area of this whole shaded inside area of the circle. I've got my fraction times my area formula. So length of the arc is fraction times the circumference, the distance. Sector area is fraction times the area. And I just plug it in. 135 out of 360 times pi times 12 squared. And again, I'll show you both ways here. If I want to just type that whole thing in and get a decimal, I can do that. And it would be 169.65 if I rounded it. And if I wanted it in terms of pi, all I'm going to do is just move that pi to the end. It would be here, but I'm not going to write the pi. Because the pi is just at the end, I'm going to move it to the end. And then I've got 54, but the pi is still hanging out at the end. So those two numbers are the same. Those two numbers are the same. Just one in terms of pi and one in terms of as a dozen. And just a reminder, this is linear units, things like centimeters, centimeters square, or centimeters, inches, meters. These are square units, so things like square centimeters, square inches. And then I'll just leave that up there. Make sure we talk about this. Just a reminder, arc measure is always in degrees. That is just the same as the central angle. The arc length, imagine actually trying to walk along that thing. It's how far you would walk. That's measured in linear units, inches, centimeters, yards, miles, whatever. That's your fraction times your circumference formula. And then sector area, this is how big that shaded in part, might not be shaded, but how big that area is, a little pizza pie slice. So this is a fraction of the area formula. Right? We're just taking pieces of circles, so it's always just a fraction times a piece of a circle. That's all this is.